Hello, Mr. Long. This is FRQ number 2. So, for part A, it's asking about the free body diagram. So, draw this box. There's a surface, so it's got to be an F of G. And also, what's opposing it is F of N2. And there is also an applied force, so I'm going to put applied force. And this thing got friction too, so what's like opposing this force here being applied is an FK, and the reason why the FK is smaller than the F is because if this FK is bigger, this box ain't moving because there's too much friction. You know, there needs to be enough force to overcome the friction opposing this. So yeah, that's the free body diagram. For part B, it's asking calculate the kinetic friction force. So we already know that mu k equals Fn, and also not Fn. Mu k equals Fk over Fn, and if we have to calculate Fk, right? So we're gonna rearrange this, you know, by multiplying this to top the Fn onto top. So now I'll give mu k F of n, and then using, you know, what's given in the problem. Sorry, my phone's shaking a lot. We got a mu of 0.2. that got no units at all. Fn has has newtons as its unit, and the Fn is already given in the problem, 44.5 newtons. So if we punch this in a calculator, 2 times 44.5 should be given 8.9. So Fk equals 8.9 newtons, and that's not all. There's not asking magnitude, so we need direction, and it's negative because, you know, it's opposing the F here, like I stated in part A. So it's going the opposite direction as the applied force, aka, you know, friction is acting against it. So that's why that thing is negative right there. Part C is asking to the y. So I'm gonna put part C here so I can save some space. Part C. So derive an expression. So we're gonna try to get acceleration, because we know that if we take the integral of acceleration, we'll get, you know, velocity, and we need that for this derivative right here. So we're gonna use Newton's second law, and it goes ma right here. And to solve for the m, we're gonna use the Fn here to solve it. So we know that Fn equals Fn equals mg. So we already know that the mass is we can also rearrange this to solve for mass. So mass equals to grams over, you know, F of n. Oh, sorry, not that. It's not right. Fn over g, because we divided g out, get m alone. So we got mass we already know that the f of n is 44.5 stated in the problem. That's newtons over, and we got 9.82 acting against, we got 9.89 against, as you know, the gravity, aka the g. It's also newtons, and if you divide that out, that should be 4.54 as the mass. So 4.54. It's hard writing with one hand. Okay, now back to this formula. We know that FK is against it, so we can just do that because, yeah, equals MA. We gotta arrange this for A, so we just move the M over like so. And we know that, so I don't need to write more units, that, you know, FK is, oh shoot, the unit of F of K is newtons. The unit of mass equals grams. So we're just gonna write this out. And we know from the problem that force equals 8t squared. So we can write 8t squared minus 8.9 as the f of k. Yeah, f of k right here. By the way, that's grams. No, wait, not grams. Sorry. It's kilograms. We should also erase this mistake. Accidentally put G. We're gonna put kg because that's mass, and we're gonna put that over the mass that we just got, aka 4.54 kilograms, not grams. I'm an idiot. So 4.54, and then that will give us acceleration. So that'll give the, my bad, that'll give the acceleration function. So if we simplify this up a little bit more, we should get a coin calculator. So 6. We're just gonna simplify so that when we take the integral, it won't be a pain in the butt to do so. Now we're gonna need to take the integral of acceleration to get, you know, the expression we wanted, kv. So acceleration, the integral acceleration is the v of t of the function, v of t d of t. So if we do that, LV of t, and already beforehand I already simplified, but you would do, you know, since it's an integral, so you're going to take that power, so 2 plus 1, so that'll be t to the third divided by 3. 1.76 divided by 3 should give you 0.59 t to the third. This thing is also going to be out of power, it's an integral, so minus 1.96 t, and it's going to have a plus c. Now we need to, and then, you know, in order to solve for, you know, c, right, the velocity function here, right, its initial speed, or the initial velocity, aka vi, is 4, and initial speed means the time is 0. So this, all these t's will be equal to, you know, all these t's will be 0. So this will be out, this will be out. So they'll be left with, you know, c, right? And since velocity equals to 4, it will also equal 4 right here. All these t's are out because initial speed, time is 0, you know, it's not moving yet. So c would equal to 4. So we're going to rewrite this expression, but we'll replace the c with the 4. So we're going to put 0.59 t to the third minus 1.96 t plus 4. And that will be your, shoot, let me just, sorry, I'm going to waste, just write dx dt. Got your expression right there, 0.9, whatever. It's also your velocity too. So that's part C done. So now to knock off part D, we want the term of magnitude when we already have our VOT function right here. So all we need to do is plug in 3. So I'm going to write out the VOT function again. VOT equals, according to the last problem, is going to be TO3 minus 1.96 t plus 4. And since it's instantaneous velocity, we can just plug in the number right here. So v, so it's asking for when t equals 2 seconds, so we're just going to plug in 2, just plug in 2 into the t because it's asking for 2 seconds. And according to the calculator, I already pre-calculated all of this before, according to, is equal to 4.8. And the units for velocity is meters over seconds. So that will be part D. That's not that bad. Part E, oh, that's part CD. So now part E, I'm getting sidetracked. Part E is asking determine instantaneous speed when the position is 2. Okay, so we want to set the position equal to 2. So in order to do that, we need the position function. And the position function, in order to get that, is the integral of the velocity function equal to, sorry, I forgot part D2, it's instantaneous. So let me just put the absolute value sign, even though that doesn't really make a difference because the answer, no matter what, is going to be positive. So, yeah. So for part E, anyway, the velocity function, we want our position, so we need to take the integral of that. So that'll give your, you know, yeah, that'll give your position. So your velocity function is already 0.9. So we just got to integral that again. So if we take the integral of that, should be able to get 0.49 t to the 4. It's just the same process as the integral as the last problem we did, aka part C. It's the same process. And it's a plus. And in order to find C, we're gonna need to set that equal to 0. C is 0 because, you know, we gotta, if you plug 0 for all of this right here, that'll just equal 0 because all the times is 0 because it's initial. So yeah, t equals 0, plug 0, all of it, all of these are out. C goes oh, right here, C will equal to 0. So we're gonna just rewrite this again. And this time we're gonna set this thing. I'm gonna waste this VOT. So we already know the position at t equals 0, aka xi, or what? Sorry, not xi. The problem states that it wants us to find when the position equals 2 meters. We want to find the time when it went a distance of 2 meters. So instead of the x of t function right here, do that. We're just gonna put 2. So I already set this up on Desmos. So I put it up, you can see, just put the function of whatever this is right here. You just gotta move this 2, that'll be -2. That's how this thing has -2 here. It's intersect at 0 right there. It says 0.56. I'm gonna round to 0.57. That's the time. So we're just gonna put t equals to 0.57. Now we got the time. Now all we need to do is plug it back into velocity. So velocity, according to the function we found right there, that's our velocity. V of whatever the time we just found, 0.6, let me just put a seconds right there. V of 0.57. Now we just gotta plug in everything. That needs absolute value sign because that thing is an instantaneous speed is 0.59. Plug in 0.57 right there. 1.96 t plus 4. And if we calculate this, I already pre-calculated it, you should get a value around like 2.999 something, but you know, I'm just gonna round it. And you know, velocity as meters per second as the unit. So that'll be your answer for part E. Now I'm just gonna turn this around so that we have more space. So part F asks to calculate the average speed. So that's not that bad. We already know that speed equals distance over time. And we already know that the time is 8 seconds. So you know what, just so that I don't need to write the units, I'm just gonna write here on the side, just somewhere right here, that t, aka what we just found, that's time. So the units for t is seconds. Distance, that's d right there. Distance equals meters. Yeah. Okay, so speed equals distance over time. We already know that the time is 8, but in order to find the distance, in order to find the distance, the integral of your velocity function, the absolute value of velocity of dot, and you know, there'll be a time here, there'll be like a time final, time initial. That'll be, actually I don't even need to write that, I can just write this because it's going from the entire 8 seconds. So from 0 to 8, how much? V of t right there, the absolute value of V of t will equal to distance, because the integral, the absolute value of the integral velocity will give you distance. So with this information right here, we can just plug and chug in this value right here. So instead of d, we already have d right here. So the integral of 8, 0 of the absolute value of v of t over your time. In this problem, it's calculating the average speed for the entire 8 seconds. So we're just going to put 8 in there. So that will equal, I can just also calculate, I'll calculate this one so I don't need to show on the paper, but it's really just, it'll look like this. So the fraction, if you can even see it, it's a little blurry. You know, our velocity function again is, I can refer back to it, 0.44 x to the 4 oops, that is not the right one, that's position I'm tweaking out right now. It's 0.59 x to the 3 to the third power, my bad, minus 1.96 x plus 4x, and that's your distance right there, and we're just going to divide it by time. So that will give a value about around 71.68. So that will equal 71.68 meters over seconds according to the calculation we have. And now I'm gonna get a new paper because part G is asking for a graph, so that's gonna take a lot of room. So it says graph the velocity. So before I put a graph, I know this thing wants to calculate all the velocity. We already know, I'm just gonna put my calculator there. We already know from the previous problem, right, that velocity equals to 0.59 t3 minus 196 t to the 4, plus 4. So now we're going to need to plug time from 1 all the way to 8 to graph it. So before we do that, v of 0 is 4 because in the problem it gives your v initial, so that'll be 4 meters over seconds. V of 1 will give if you plug in here, so you plug in here 0.59, 1 to the third power, minus 1.96, 1 plus 4, it'll give value 2.36, which is smaller than the initial. And then for V of 2, that will give you, if you plug in again, and this is very tedious, just gotta plug it again. That'll give you 4.8, so just a little bit bigger. And then now if we calculate V of 3, give you a value of 14 point, just checking, make sure my work is right. V of 4, again, is 33.92 meters over seconds. V5, again, they'll give you, geez, it's hard to write, 5 meters over seconds. Holy, this, I'm just gonna put V6 down here. It looks pretty awkward, but it is what it is. 596 to the third power, 6 plus 4, 119.67 meters over seconds. V of 7 again, but just plug 7. Give you value 192, so 192.65 meters over seconds. Last one, V of 8 equals 0.598. to the third power, minus 196 to the 8, plus 4, 290, 290.4 meters over seconds. And now we're gonna put the graph, so I'm just gonna, this is shaky. We just put my thing up there so I have more room. Whatever, it's a big, Jesus Christ. Okay, that's not straight at all, but that's what the graph looks like, yeah. Your y-axis will be your V of t. That unit is meter over seconds. Your x-axis will be time. If I can write with one hand, that's seconds. Okay. Now we're gonna put 8 points here because this thing went for 8 seconds. So 1, 2, 4, 5, 6, 7, 8. 2, 3, 4. Okay, so now for drawing it. So this is the origin, V of 0. V of 0, according to the calculations, not calculation, the problem is around 4. So I'm just going to put a little here. That's 4, whatever. V of 1, 2.63, so it's going to be a little bit lower. It's not exact, but it's not drawing the scale, so whatever. V of 2 is 4.8, so just a little bit higher than the 4 there. V of 3 is 14, so I'm just going to put like a 14 right here. 14, so just a little bit above it, not exact. It's not going to be exact really. V of 4 is 33.92, so I'm just going to put just a little bit bigger right here, probably 33, and just a little bit over. Should be good. So 33.92 seems exact enough. V of 5, 67.97, so we're just going to put 67 right here. Actually, I want a little farther. That's not really. Let's put 67 right here. 67. Just a little bit above. 67 right there. V of 6 is 119, so that can go right here, I guess. 119 V of 6 around here. So yeah, that thing is growing. V of 7 is 192. Just put right here. You don't have enough space to fit really. 192, whatever, can go here. It's not exact, but just so that we can fit everything here. 192 is right here. 7 can go right here. And the last one is V of 8, 290. So we can just put right here. It's a little bit above right here. Doesn't, but it should be like an exponential growth. So just gotta connect this. So yeah, that is gonna be the velocity as a function of time. That's your V of t graph. That's what all the velocities that we just calculated using our V of t formula that we calculated in letter C. And sorry, this is very shaky, but it's very hard to write with one hand. And yeah, see you. Before I also go, I drew this integral thing wrong somehow. I don't know how, but just whatever, just put parentheses over it. I just set up my integral wrong here, or the integral step its way. It's just I wrote it wrong. I put the dt on the like a weirdo, so that will equal. Let me erase that real quick. dt dot equals v of t. So yeah, that's what an integral should look like. Yeah.